Assalamu alaikum. In this lecture, we are going to talk about the differential protection scheme with the effect of actual CTs. In the last lecture, we defined the zone of protection in case of a differential protection scheme, which was defined by the CTs at the ends of the equipment that is under protection. So whatever is inside the two CTs is known as the zone or the closed zone of protection, and all the faults that are within the CT's jurisdiction, that is known as internal fault, and the one that are outside the zone of the equipment that is under protection or outside the boundary of these two CTs is known as external fault. Now, all the discussion that we had in the last lecture, that was specifically directed towards the ideal CTs. So that's why the discussion about the differential scheme in the last lecture was about ideal differential scheme that can pick the smallest of the internal faults. So if we have the fault in this zone, that can be picked by the protection scheme and will not work for the largest of the external faults, because in that case the current that is passing through the relay will be equal to 0. But there are some limitations that are associated with the CTs. The first one is that there is always a ratio and phase angle error when we are talking about the secondary current of the CT. What does it mean? If we draw the equivalent circuit of the CT, this is burden, this is Z secondary, Z primary, and this is the XM, and there is one resistance here as well, that is RC. So this RC represents the core losses and XM represents the magnetization losses. So this is a circuit of the CT when the primary of the circuit is actually referred to the secondary side. So now if there is a current that is passing through the primary winding, then it is divided into two parts at this node. One is I2, which is the secondary current, and the other one is I0, which is actually the current of the magnetization branch. So I0 is the current of the magnetization branch. So there is always a mismatch between the current that is measured at the secondary of the CT in reference to the primary current, because there is a current I0 that is required for the magnetization branch that should be represented in this I2 in order to exactly calculate what was the I1 in the primary of the CT. So therefore there is always a error in the measurement of the CTs, and as this branch is actually highly reactive, because this XM portion of the impedance is the dominant one, so there is always a phase angle error whenever we are implementing the actual CTs. Moreover, there is a burden here that actually represents the pilot wire resistance and reactance, as well as the relay resistance. So the error of the CT is actually dependent on the burden. So if you have to reduce the error, you have to keep this burden equal to the rated burden of the CT. So there should be minimum error between the actual value that has to be measured and the value that is being given by the CTs. And then there is another thing that happens when we have large external fault currents. For example, we have a fault at this point, and there is a large current flowing at point A due to two generators, for example. So there is current feed from two different sides. One from this side, the other one is from this side. Or you can take any other example in which we have large external fault current flowing at point A, but it is outside the zone of the protection scheme, so the relay should not operate, or the differential protection scheme should not work in the case of fault A. As we know that in CTs, if there is a current I naught that is flowing through the magnetization branch, so there is always an error. So if the fault current increases, this error also increases. So if this error increases, then the spill current that is actually passing through the relay, it will also increase, right? So error increases as the through fault current increases. So with the increase in the through fault current, the spill current increases, and there is a chance that in some cases when the fault current is so high that the spill current may have a greater value with respect to the plug setting of the overcurrent relay that is being used in the differential protection scheme. So if the spill current will be greater than the plug setting of the relay, then the relay will operate, but this is a external fault current, so the relay should not operate, right? So these are the few limitations that are being introduced by the selection of the actual CTs, or the ones that are practically used. So if we have to look at it in this diagram, we have an equipment. The current is fed by a single generator and the current is IP, and there is a fault that is occurring outside the zone of the protection scheme. There is one current IS1 that is flowing in the secondary of CT number 1, and the current IS2 that is flowing in the secondary of CT number 2. So this IS1 is actually IP divided by N1, which is the turn ratio of the CT. If the current is entering this dot, the current will be leaving this dot, and this current will be approaching to this node, and the current at this point is IS1. Similarly, the current through this CT is leaving the dot, then and in the secondary of this CT the current will be entering the dot, so this current should be IP over N2, right? So there are two currents, IS1 that is flowing opposite to the direction of the actual current, the primary current. Similarly, IS2 is also flowing opposite to the direction of the primary current. So in both the cases, the secondary current is 180 degree out of phase with the primary current. So that is represented in this phasor diagram. So the IP is in this direction, primary current, and the secondary current is in this direction, that is 180 degree out of phase. That should be the scenario when we are not considering the magnetization branch of the CT. And we know that the magnetization branch has a current I naught that is flowing through the magnetization branch of each of the CTs that is being used in the protection scheme. And this I naught is actually comprising of two different type of currents. One is IM that is passing through RC, which is representing the losses, and then there is IW that is representing the magnetization losses and is passing through XM. So if I will draw the phasor for I naught, the resultant will be, this will be your IM and this will be your IW, and the summation of these two phases will give you I naught. So if you have IP in this direction, then this will be your IS and this will be your I naught. So I will draw this one again. So this is your IP. So IP is actually the summation of IS and I naught, and I naught comprises of two different currents. One is IW, that is passing through XM, which is representing the magnetization losses, and IM, that is representing the current that is passing through RC, which is actually the representation of the core losses. So now if we come back to this phasor, the IS1 and IS2, both of these currents were 180 degree out of phase with respect to IP, and this should be the case when we have only resistance in the magnetization branch of the transformer. But we know that we have another element, that is XM, and due to this XM we have a phase difference θ1 and θ2 in IS1 and IS2 respectively, right? And if I have to find IS1, that will be the summation of IS2 and spill current, because IS1 is actually coming to this node and this current is different from this current. Therefore there is some current either going into this relay or coming from this relay. So this actually IS1 is actually the summation of spill current. Spill current is the current that is passing through the relay, and the secondary current IS2, right? Hopefully you have understood this phasor diagram. So in case of fault current, the external fault current, there is a spill current through the relay that is represented by this phasor and the adjacent diagram of the differential protection scheme. Now if we look at the equivalent circuit of the CT, we have the primary current IP, and this dotted rectangle is actually showing the ideal CT. So if the current IP is entering this dot, then the current IP by N is the turn ratio of the CT, will be leaving this dot, and at this node there is a current I naught, that is the current of the magnetization branch. This one, there is a inductance and resistance in the magnetization branch. So now after this node we have a current IP over N minus I naught, that is actually the secondary current, and this IS will be passing through the Z burden, that is actually the summation of the pilot wire impedance and also the relay impedance. So after passing through this Z burden, there is the secondary resistance and reactance of the CT, and when we come to this node, the current I naught is coming from this direction and IS is coming from this direction, and both these currents are flowing towards this node. So the summation of these two current will be flowing after this node. So if I naught is coming from this node, I naught plus these two I naught will cancel out, and IP over N will be the current that will be leaving this node and will be passing through the primary impedance of the CT. Now let's look at the implementation of actual CT in the differential scheme. Now we have two CTs, CT1 and CT2, that are connected in the similar configuration that we have discussed in the last slide. We have an external fault IP, so there will be the same current flowing through both the CTs. At this point the current IP will be entering the node, the current IP by N will be leaving the node. At this node there will be the partition of the current. One is going to the magnetization branch, that is I naught, and for CT1 we are saying that is I naught 1. So the current that is leaving this node is IP over N minus I naught 1, and this current will be coming to this node. Starting from this CT, there is one current in the dot, so the current IP over N will be entering the dot, that is being represented here. Similar to this magnetization branch, there is another magnetization branch for this CT, so every CT has its own magnetization branch. So the current I naught that is represented by I naught 2 for the CT2 will be coming to this node. So IPN should be added with I02. So there will be a subtraction of I02 from IPN if we have to move away from this node, right? So the current that is passing through this wire is actually IP over N minus I02. And the differential of these two current, that are one current is entering this node and the other one is leaving this node, so the differential of these two current will be passing through the relay. That is known as a spill current. So if you subtract these two currents, you will get I02 minus I01. So the current that is passing through the relay is actually the difference of the magnetization branch currents of two different CTs that are employed in the differential protection scheme. And after that, this is the pilot resistance, and these are the resistances of primary and secondary windings. And this part of the circuit is actually the replica of this portion of the circuit. So from this explanation we get that through the relay we have a spill current that is actually the subtraction of the magnetization branch currents of two different CTs that are applied in the differential scheme. Now we came to the conclusion that in some cases when the external fault current is so large that due to the error of the CT, we will have the spill current through the relay that will exceed the plug setting of the relay. So we have an overcurrent relay and it has a plug setting which is represented by this line. So if the current through the relay, or the spill current that is passing through the relay, is more than this plug setting of the relay, then the relay will trip. So we have defined this region as the trip region. But if the current is less than the plug setting, then it will restrain. But as the through fault current increases, this is the current for which relay should not operate, the spill current increases gradually, and at some point the spill current will be more than the plug setting of the relay, right? So after this point, during this portion of the line, the relay will trip for the external faults as well. So that is actually the loss of stability for the differential protection scheme. And that's why we usually do not use the differential protection scheme. We use a percentage differential scheme. Percentage differential scheme, in which we actually tilt this line slightly. By using this tilted line, we know that the region above this line is actually the trip region, and the region below this line is actually the restraint region, right? So we have to add some extra restraint to the differential scheme so that if the external fault current increases, the restraining torque should also increase. And by doing so, we are actually getting this extra margin for the through fault current. And this percentage differential scheme will be discussed in the later lectures. Now, in order to increase the stability ratio, what we can do, we can increase the numerator or decrease the denominator. So maximum through fault current beyond which the circuit mal operates, divided by the minimum internal fault current that is required for tripping, which is actually the plug setting of the relay, is known as stability ratio. So if we have a higher stability ratio, it means that the scheme will be distinguishing between the external and internal fault currents, and also the phase angle will be reduced, because higher stability ratio means the CT are closely matched. CT are closely matched, so there is less error, so the phase angle error will be reduced, right? Lastly, there are some drawbacks that are related to the differential protection scheme, that during the large true fault currents we have spill current that is actually more than the plug setting, which is substantial, and it will operate the relay falsely, and we already have discussed that. But in case of transformer, we have different voltages on its both sides. We have V1 here and V2 here, so we have different primary voltage as well as different secondary voltage, so we have to use CTs that have different turn ratios, right? And it is very difficult to have a close match between the CTs. What we can do, we will try to operate the CT as close as to the rated burden, so that they are closely matched and there is very small error between the two CTs measurements, right? So we have different CTs will have error that are different, and due to that we will not be able to get a close match. And if we don't have a close match, it means that there will be a large spill current in case of through fault currents, right? In case of bus bars, we have large number of feeders. For example, there are 2 incoming feeders and 4 outgoing feeders. But in case of fault, for example, we have a fault on this line. The current will be flowing from all the feeders to this faulty point, which is, for example, A. So there is one current flowing from this feeder, one from this feeder, the other one from this, and the last one from this. So in case of a bus bar, we have large through fault. So if it is a large through fault, it means that we have large error. There is a mismatch between the CTs, and due to this problem we will have large spill current, and this spill current will be greater than the plug setting of the relay. So we have to make the differential scheme specifically for the type of equipment we are using, right? So in case of transformer, we have a protection scheme with different setting, and for bus bar we have a differential protection scheme with a different setting. So the setting of the differential scheme should be equipment specific. Thank you.